Let's go. Let's do this. What we're going to do is figure out how we can write this as a definite integral. Okay, so here's what we're going to really be dealing with. Hopefully you noticed in this definite integral that we have, well, some new vocabulary that we'll dig through a little more later. But we have an interval, so we need to know our interval, okay? We also need to know what the function is, and then if you're like, what's this dx? It is something that we'll encounter later. Right now it's nothing to worry about, but it's part of the notation. It's actually an operation that we do. It looks like times dx. It's sort of treated that way, but it is an operation we do that tells us that we're simply dealing with an x. And we will be dealing with an x and not a y or any other variable, okay? These two variables should agree in Calc 1 for now. We're good. So there might be both thetas, they might be both y's, but they will agree. Things change later, but we won't play that game. So here's what I need. I need a final answer. So let's just go ahead and start writing a final answer. And my final answer is going to involve something that's written hugely in red. And hope you can see that okay. And actually, just in case you can't, let me write it in black. What I really want to do is figure out, that's huge, I want to figure out the interval that I'm dealing with, okay? So I'm going to identify certain pieces of this that'll come in handy, and we'll just switch colors here for a second. I hope you notice that delta x is pi over n. I just would like to think that that's going to come in a little bit handy in what we notice. So I'm going to walk over here, and we're going to say that delta x is pi over n, and that's good to know, and I'm happy with that. But that's going to help me figure some stuff out, right? So let's see, well, delta x is really b minus a over n. So we have b minus a, and it's divided by n. So using a little bit of common sense, we know that pi is equal to b minus a. Okay, all right, fine. So here's what we do know so far. Our interval is pi units wide. So whatever this is, what we are trying to do is figure out what function is being represented here. So we have, same kind of picture I draw all the time. We're trying to figure out where does it start, where does it end, and what is this function? That's what we want to know. Where does it start, where does it end, what is this function? Let me point and say that again. Where does it start, where does it end, what is this function? So let's go for some obvious. The function involves cosine. Where does it start, where does it end? I don't know, but I know it involves a width of pi. So let's go for something else that's a little obvious. It's going to trip us up on the next one if we always jump to this conclusion. But here's what's happening. We have f of our input. So in the original structure of this, we have f of x, and in this case we have cosine of x, whatever it is. So the function itself is cosine, which means that a is pi over 2. Okay, the next one's going to trip us up if we follow some of those lines of thinking like this, but for now let's just kind of look at this and say, well, what's happening? I am cosining x, okay? Well, f of x. This is my input, so this has pieces that correspond to that. So a is pi over 2. I think that's very good to know. Let's just come over here and say, well, a is pi over 2, which actually helps me figure out b. I'll go ahead and tell you it's 3 pi over 2. Let's figure it out. Let's use blue. Let's close. Let's recap. We're going to put pi here. We're going to put b minus pi over 2. We're going to add pi over 2 to both sides, and we're going to figure out what b is, 3 pi over 2. And so we know that our interval goes from pi over 2 to 3 pi over 2. I'm going to pause here for a second. I'm talking fast, saying a lot of very clunky notation, a lot of new things that you're digesting. I almost said digressing. It's like, what, squirrel? But we are digesting a lot of new things, particularly this. So let me say it again. Where do I start? Where do I end? What is my function? That's what I want to know. What about the dx? Talk about it in another lesson. It's just an operation that we do. So 3 pi over 2, and then I'm going to have some function and a dx. Right here is going to be f of x. What is my function? What function am I really dealing with? Okay? I need to identify my input. My input was all of this. This is my input into the function. Now, if we want to continue to identify certain parts of this, we could say, well, there's my k. See? All right. So k is accounted for right there. There's my k. And then delta x is pi over n. I sort of already knew that. Delta x is pi over n. So these are already in there, and delta x shows up here as well. So it's all accounted for. So we really have a function that is the cosine of my input, which we'll call x, for that reason. So this is my final answer. Okay. At the bottom of the notes, or near the bottom of the notes, it says, write each of your right Riemann sums above as a left Riemann sum. Whoa, okay. As if this wasn't overwhelming enough. So far, we have taken this ridiculousness, determined the width of the interval to be pi, boom, found where we started because a was pi over 2, therefore we could find where we ended, and then we said, oh, cosine of input, cosine of that mess, cosine of all that stuff that looks so clunky is my function, so cosine of x, and that's it. But if this was a left Riemann sum, how would it look different? Okay, so this is one of the answers. This is one of the things they asked for. At the top of the paper, it says, express each of these right Riemann sums as a definite integral. Done. Slide down below the problems. Write each of the right Riemann sums above as a left Riemann sum. Not done. So, erasing a little bit, switching colors. What they gave you was a right Riemann sum. This right here is a definite integral. There will be a big lesson devoted to this later. Whole lessons devoted to this. It's beautiful. Definite integral. That will, this whole thing right here is a definite integral. I'll circle the whole thing. But what I don't have is a left Riemann sum. And we're about to come up with that. So we're going to call it a LRS, left Riemann sum. And my left Riemann sum is going to look very similar. So we're just going to start walking through it and figuring things out as we go. So we know it involves a limit as n approaches infinity because we really want to have an infinite number of rectangles. And we're going to start at 1 and we're going to go to infinity, and we know we're going to have a cosine, but now we got to figure out the guts of this thing. We also know this, pi over n. Okay. So here's what's going to change. Our input. Whenever we were finding a right Riemann sum, we would, and I'm running out of space here, work with me, I'm going to squeeze a little graph in right here. If I was finding a right Riemann sum, I would not start on the left. I would start one rectangle away from the left. Right? Okay, talked about it. Now that I'm starting with a left Riemann sum, I will start on the left and I will end one width of a rectangle away from the right. So if I want to start on the left, then I start at A, which in this case is pi over 2, which means I need to put a pi over 2. And then with each step, every step I take, just like Sting, with each step, it's a song. With each step I take, I'm going to be adding one more width of a rectangle. So I know I'm going to have pi over n. That's the width of the rectangle. So far, this really doesn't look too different. But here's the thing. On the left, on the right Riemann sum, I started one unit away. But now I want to start 0 units away. So I won't start at 1, I want to start at 0. An easy fix for this would be to put a 0 right here. We'll fix that in a minute if we want to do it a different way. Or I could say, you know what, let's just back this up 1. It works the same. Okay, this is a left Riemann sum, or we can do the exact same thing. Oh my goodness, that is the ugliest sigma I've ever drawn. It must be erased now. The limit, that's the ugliest limit I ever drew, n approaches infinity of k equals 0 to n of the cosine of pi over 2 plus, and then it's going to look exactly the same because then I would start with 0 here, which means that I'm going to truly start with the cosine of pi over 2, which starts me on the furthest left, which is the left Riemann sum. That is a pi over 2, by the way. Let's make it look more like that. Pi over 2 plus pi over n times k. We'll put the k up there. And then pi over n. Okay, there's a whole lot in this first video. Whew, that's a lot. It's a lot of new notation, a lot of new stuff. It's a little overwhelming. We have 3 more examples to go. They'll go a little quicker.